Okay, let's talk about some properties of metals, which we are kind of familiar with, right? Metals are shiny, the metallic luster, right? Um, they're malleable. Malleable. That means you can take a hammer and you can pound them, and they'll hold that shape as you shape them. All right. Here's an example of somebody with sodium metal. Have you ever seen a chunk of sodium metal? No, I don't think I have. So here's a chunk of sodium metal, and they are using a chisel to break open that chunk of sodium metal. Notice that on the outside of the sodium metal, there's a white, kind of like, looks like brie cheese almost, some white material. That is the surface of the sodium interacting with the moisture, the oxygen in the air, and creating sodium oxide. But inside you can see is the shiny metal of sodium, and you can see the malleability. Now, when we talk about metals, you might look around, you might see your ring, you might see some piece of jewelry or something, some metals on the chairs, tables, so forth. These are not elemental metals. These are combinations of different metals to form alloys, right? And elemental metals have this property of being malleable. Metals, the way that we think about them, are not malleable, right? A baseball bat, a metallic baseball bat, it doesn't bend when you hit it on the ground, right? Chairs on the table, they don't slowly bend. Our rings, our jewelry doesn't bend. And the reason is because it is, again, um, what we call uh, metal, like I'm drawing a blank. What do you call metals when they come together to form new compounds? Alloys. Oh yeah, alloys. Alloys. That's right. Thank you. Alloys. So gold is an alloy of, sorry, jewelry is alloy. Gold jewelry is an alloy of gold and some other metal, right? Usually something like silver or copper or something like that. Um, so what do you think? Do you own any jewelry? Yeah, I have some. Do you know, did you remember when you bought it what carat it was, or if they talked about it was a gold jewelry? Yeah, I have a gold ring. Is it, do you remember the carats? I think it was a 10 or 12 carats. All right, yeah. So 24 karat gold is what they consider as pure gold. And you don't find much jewelry from 24 karat gold because it's so malleable. Okay. However, you will find 12, 10, 14 karat gold that is increasingly malleable as you get closer to 24, but still stiff enough that it's not going to lose its shape and structure. Here's a video of placing that piece of sodium into water. Okay. So when the sodium goes into the water, it reacts relatively violently. And if you were to take the pH of that water that the sodium just exploded in, you would see that it had changed slightly, depending on the volume. It had changed to a more alkali pH. Now, we don't know what alkali is necessarily. It's not a word that we use a lot. But alkali refers to the opposite of acidic. So you've heard of the word acidic, and alkali is the opposite. And that's where we get this term, the alkali metals. You put them into water, and they result in alkali water. Okay, so nonmetals, basically the properties that metals don't have. They're brittle. They're not malleable. They don't conduct electricity. That's another one that is important. Metals conduct electricity. All right. Um, when you hit them with a hammer, they shatter into all sorts of pieces. Okay, metalloids have very interesting properties, and again, these are our staircase along our periodic table here. Uh, Boron, silicon, germanium, right? These ones down in here. Very interesting properties. When we discovered how we can harness the property of silicon to store data, because with an electrical charge, it has a metallic property. Without, it loses that metallic property. So we had the ability to store and retrieve data off of silicon wafers like this. It changed the world, right? We could store data and retrieve it and store a lot of it. And we've gone on to improve our ability to store data and create semiconductors as well, which will conduct electricity under given conditions. All right, so a huge, huge leap. Um, If I could make my computer out of germanium, the computer would be significantly faster, but it would be also significantly more expensive. Okay. All right. Some of our chemical names have symbols that are not the same as our English names, and that comes from the fact that their initial Latin names were different. Okay, so focusing now on molecular and ionic compounds. Okay, molecular compounds, or let's start with ionic compounds. Ionic compounds and molecular compounds differ in the way that they interact, their electrons of their uh, compound partners interact with each other. So here's an example of an ionic compound. Water, our example of a molecular compound. All right. We could tell this is an ionic compound. How could you tell this was an ionic compound, maybe, Fred?
Well, can you bring back the periodic table?
What do you need to look there?
Well, looking for sodium's a metal.
That's right. So if the compound contains a metal, then that's how we can tell that it's an ionic compound. That's an easy way to tell that it's an ionic compound. So we have this ionic compound. And the way that this ionic compound forms is you have a sodium atom and a chlorine atom, for example, combining together. And when they combine together, an electron goes from the sodium to the chlorine. And you result in a sodium with a positive charge and a chlorine with a negative charge. These two now are atoms are ions, and those ions come together to form sodium chloride. Okay? So in this case, an electron has been transferred from one element to another. In the case of water, oxygens and hydrogens share electrons, and we'll talk about how that sharing occurs in future chapters. But electrons do not completely transfer from one element to another, but there is a sharing. And this sharing results in molecular compounds, also known as covalent compounds. Covalent and molecular is an indication that the electrons are being shared, not gained or lost. When you lose an electron, sodium I atom goes to sodium ion. The size of the atom or the resulting material, the element, species is a better thing to call it, right, decreases. If it goes to a positively charged ion, it decreases. If it goes to a negatively charged ion, like in the case of the chloride atom, here this would be maybe the nucleus and the electrons on a chloride atom, whereas the nucleus and the electrons on a chloride atom would be larger. Chloride ion, sorry, will be larger because we have an extra electron. Okay? We'll talk more about that in the future as well. We also have what are called polyatomic ions. Polyatomic ions. Now, polyatomic ions, they are groups of atoms that come together to form ions. Now, here I brought up this table of polyatomic ions. It's a little bit bigger. It's the same table as here on this slide, but it's a little bit bigger so we can read it a little bit bigger maybe. Okay? And this list is not an exhaustive list. That means there's a lot more polyatomic ions that are out there. This list is on the back of the periodic table that I gave you guys, right? So in many classes, generally you memorize the polyatomic ions. And my experience teaching over many years is that when we memorize the polyatomic ions, they go into a certain kind of memory that's good for getting us a great grade if we're good at memorizing it at one point. But then at the end of the course or into the next course, the memory doesn't work as well. In fact, if anybody does really remember the periodic or the polyatomic ions, it's because of use and because of being exposed to this list over and over and over, not just for 1 week throughout their life or at the beginning of their term or wherever. So what I want you to do in this class is make a promise to me that when you come across a polyatomic ion, you bring out your sheet, your polyatomic ion sheet, which is on the back of your periodic table sheet, right? You bring it out, you find the polyatomic ion, you find the name, and you find the charge that's on it, you find the formula for the polyatomic ion, and you remind yourself of those three things: the name, the formula, and the charge. Okay? And you do that over and over and over, and the result will be a firm grasp and memory of what the polyatomic ions are. Okay? So we're trading. You don't have to memorize the polyatomic ions, but you have to promise that you're always going to get out the polyatomic ion sheet every time you come across the polyatomic ion and remind yourself what it is. Do you promise, Fred?
Oh, me?
Yeah, everybody has to promise.
I promise.
Did you say promised or promised?
Okay, I promise.
All right, good. All right, so polyatomic ions, again, are groups of atoms that come together to form ions. Some examples, right? Let's look at the sulfate ion, SO4 2 minus, right? It looks like this. Its structure is S with 4 oxygens around it, all right? And 2 of these oxygens have a negative charge on them, like that. So that's an example of a polyatomic ion. We don't need to know the structures. We'll learn the structures later on and how to identify what they are, but for now we're going to want to know the chemical formula and the charge on them. All right? If I'm going to form a compound between sodium and sulfate, I can use the periodic table to identify what the charge will be on the sodium ion. What do you think, Fred? What will it be?
In that first row, it's +1. It has 11 protons, 11 electrons to start off. And when it forms an ion, it's going to want to have a noble gas electron configuration similar to neon, which is 10.
Okay, so it's going to result in a +1 charge. So sodium is going to have a +1 charge. The sulfate has a 2 minus charge. I'm going to need 2 sodiums to balance that charge to create a compound, which is going to be sodium sulfate. Sodium, sulfate, sulfate, sodium, right? Easily named. These compounds are easily named when it's just a monatomic ion combining with a polyatomic ion. All right. We talked about ionic bonds, covalent bonds, ionic compounds, metals, nonmetals, readily gain electrons from anions, right? So here's another thing we talked about. Sodium taking an electron or giving an electron to chlorine, forming the ions. All right, let's show here an example of sodium reacting with chlorine gas. Here's chlorine gas in this bottle. This is sodium. We're taking the piece of sodium and we're putting it into here, into the chlorine gas. Notice initially it doesn't react, and kind of like gasoline and oxygen. They don't interact to start off with. You need a match to get that gasoline and that oxygen to work. Here our match is just a small drop of water. And the small drop of water, what it does is it begins to react with that sodium, and then when there's enough heat, that allows the sodium to start reacting with the chlorine gas. So a little bit of heat is produced, and then we have a reaction between sodium metal and the chlorine gas. All right, so we lost that video for a second there. But this white haze, what do you think that is? After the reaction occurs here, what do you think that white haze is, Fred?
Is that sodium chloride?
That's right, it is. That white haze there is the sodium chloride salt forming. Okay, good stuff.